So chapter 14 is about rational functions. And this is largely an Algebra 2 review topic. So a rational function is something that could be written in this form, P of x over Q of x, where P of x and Q of x are polynomials, and Q of x is not 0. Why don't we allow Q of x to be the 0 polynomial? Because it'd be in the denominator of a fraction. We know that's very, very bad. All right. So first thing we'll talk about is domains. So let's say we have this function f of x equals x plus 4 over 2x minus 1. And we're looking to find the domain here. Notice the only operation going on that could potentially be a problem is the division. And when is division a problem? When you divide by 0? Yeah, so all we'll do is set that denominator not equal to 0, because we know that x cannot equal 0, or the denominator cannot be 0. So when we solve for x, we get that it can't equal 1/2. So to write our domain then, using interval notation, so we have everything but 1/2. So negative infinity to 1/2, and then 1/2 to positive infinity. Notice we're using parentheses everywhere, implying that the 1/2 is not included in this set. Everybody happy there? NBD, right? It's like we've done this before, because we have. Okay. We'll do one more example here before we move forward. Again, still just a rational function. Again, the only operation we can get us in trouble is the division. So, same thing, we'll just set that denominator not equal to 0. To solve this, what are we going to have to do? Can be the easiest way to solve a polynomial. Looks like this. Lily? Yeah, it'd start by factoring out an x. That's great. Notice there's a greatest common factor of x. And what do you recognize after that? Well, you should hopefully see the difference of two squares there. That x squared minus 4 factors. And then you can apply the zero product property. And say x cannot equal 0, 2, or negative 2. So now we just translate that into intervals. So go negative infinity to the smallest, and then the smallest to the middle to the biggest, and then the biggest to positive infinity. So we end up with 4 intervals there. Everybody happy with that? Again, the thing to really be careful about and keep in mind is you have to make sure everything is going from small to big, right? As you're writing all those intervals, the smaller number on the left, the bigger number on the right. As you look at the endpoints, they should be getting bigger as you move from left to right. Okay. All right. So The next thing we'll be talking about is sketching a graph. To sketch a graph, we're going to just worry about some key features. So there's going to be 5 key features that we're going to worry about here when we're sketching the graph for a rational function. The first is a vertical asymptotes. So to find those vertical asymptotes, we're going to take the reduced version of the denominator, set equal to 0, and solve. The next thing we're going to worry about is the end behaviors. And there's actually 3 cases that we could fall into here. The first case is where the degree of the numerator is less than the degree of the denominator, in which case we get a horizontal asymptote or end behavior at y equals 0. Case 2 is where the degrees are equal. In that case, we get a horizontal asymptote or end behavior at the leading coefficient of the numerator dividing by the leading coefficient of the denominator. And in case 3, where the degree of p of x is greater than the degree of q of x, we're going to use polynomial division to find our slant, or sometimes it's called an oblique asymptote. So the zeros, to find the zeros, we're again going to take the reduced numerator, set equal to 0, and solve. We want the y-intercept. That's where we've just plugged 0 in for x and evaluate. The last piece is the removal of discontinuity. And again, that removal of discontinuity can happen only when reducing, and not even every time when you reduce. So it just kind of depends. We're going to run through 3 examples here for sketching. Why do you think we are going to do 3 examples? 1 for each case. That's using your noodle. Noodle is slang for brain. All right, so our first example is x minus 1 over x squared minus 4. All right, let's start by the vertical asymptote. How do we find that? Set the denominator equal to 0. Really, we should have done something else first, though. should check to see if we can reduce. Now, probably most of us can look at that and tell that there's no reducing that's possible. That the factors of the numerator x minus 1 are not factors of the denominator, which would be x plus 2, x minus 2. But we should at least make mention that we are doing that, even if, you know, there is no reducing possible, like in this case. Everybody cool there? So the end behavior, all right, we need to compare the degrees. What's the degree of the numerator? Anybody? 1, yeah. The degree for the denominator is 2. Which case are we in? 1. So that just tells us that we have our end behavior at y equals 0. Zeros, we set the numerator equal to 0. The y-intercept, we plug in 0. And since there's no reducing, there's no removal discontinuity possible. We all feel good so far? Me too. Ew. That's not what I expected. All right. All right. So first thing I'm going to do is draw in my key features. Okay, everybody's good with what I've drawn in there. Got my two vertical asymptotes. I got my end behavior. I got my 0, and I got my y-intercept. So the question becomes now, if I'm sketching, is what is the graph doing at each one of these vertical asymptotes, right? So for example, on the left side of that x equals -2, is the graph going up or going down there? To determine that, what I'm going to do is just type in some test values. So I'm going to pick a couple of values to getting closer and closer to -2 from the left side and plug them in for my x's and see what happens. Now, you could do this with a 4-function calculator just as easily as what I'm doing now. But Mr. Kulik is just going to try to be efficient since we're going to be plugging things in over and over and over to this function. I find the easiest way to do that is to type it into the y equals menu. Then I can use the function yvar, or yvars function, and then I can just use the function notations to plug these in so I don't have to like keep typing stuff in over and over and over again. It's just a little bit quicker for me. So the two values I'm going to pick on the left-hand side of this asymptote are going to be -2.1 and then -2.01. So I'm going to get a little bit closer to that asymptote and see what's going on. So I start at -7.5. Oops. And then -75. So to me, that's decreasing. So the arrow must be going down there. And since I know I'm bound by that horizontal asymptote, I know that part of the graph must look like this. Everybody cool with that? Now I'm going to do that 3 more times. One for the right side of -2, the left side of +2, and the right side of +2. So here I'm going to do -1.9 and then negative 1.99. So getting a little bit closer to negative 2 from the right. There I noticed that I went from 7.4 up to 74, so it's going to be pointing up. So I can fill in that much. Now I need to see whether I'm going to be going up or going down at the next asymptote. So I'm going to see what's going on the left side of positive 2. So negative 2.3. And then negative 24. So we're going down there because we're getting smaller each time. And then my last part is to see if I should be up here or down here. So we'll do positive 2.1 and then positive 2.01. So again, got bigger, so we should be pointing up. And there we go. Now I recognize that you could have typed this into your calculator and hit graph and gotten the same picture. The point is, though, that you could still do the same thing with just like a 4-function calculator by plugging in the values and kind of seeing what's happening near the asymptotes, right? Which is what Mr. Kulik had to do way back in the Stone Age, right after he got done inventing the wheel. So, okay. Next example. We've come a long way, though, baby. You know, the wheel, graphing calculators, space flight. You know, I did a lot. It wasn't all me. Thrag helped too. That's what I imagine a caveman name would sound like. Anyways, next one up. Vertical asymptote. What do I do? Yeah, see if I can reduce. Clearly here the degree for each of the are 1, so there's no reducing that can be done. So next, after I've checked my reducing, which I can't do, yeah, set that denominator equal to 0 and solve. Okay. Here I notice that the degrees are both 1 for the numerator and denominator because they're degree 1 polynomials. The largest exponent on the variable is a 1 in each case. So that tells me it's going to be the leading coefficient of the numerator, which is negative 1, over leading coefficient of the denominator. So just y equals negative 1 will be my end behavior there. To find the zeros, I take the numerator, set it equal to 0. The y-intercept, I'm just going to plug 0 in. Gives me 2/3. And again, no reducing, no removable discontinuity. So now it's sketching time. Okay. So drawing my asymptote, my end behavior, my x-intercept, and then my y-intercept. And if I look at, yes, Luke?
Do you mind putting like DA next to the line that is the vertical asymptote, just as like a label?
Sure, you could write like x equals -3 by it, so it's super clear what it is. Do you want me to do that?
Yeah, yes, please.
Oh, sure. There you go. Cool? All right. Oops. Okay. Notice if I look at the right side of the graph, the only way for me to connect those 2 points that I've drawn there and to not run into the asymptotes without doing something crazy is for the graph to look like this. So I only really need to check what's going on the left side of that asymptote, which is very nice. You know, anytime I can do a little less work, I am super okay with that. Right? What's that old adage? Work smarter, not harder. Mathematician definitely came up with that. I don't know that for a fact. I'm just being silly. But it sounds like something a mathematician would say, doesn't it? So I noticed that as I got closer to -3 from the left, we're getting smaller, telling me that the graph is pointing down there. So there's my other section. And I'm donezo with this one. Not so bad. All right. Last example for the sketchings. Go. So we have x squared minus 4x minus 5 over x plus 2. First thing I should do is check to see if this reduces. It's not as obvious just looking at this by inspection that it will or will not reduce. So I will factor the numerator. The two things that multiply to give me -5 and add to give me -4 are -5 and +1. If I look, no reducing possible here, so we're good to proceed. So vertical asymptote at -2. End behavior, the numerator is degree 2. The denominator is degree 1. So to find that end behavior, I'm going to need to do polynomial division. I'm going to do long division here. I recognize that this is a situation where you could do synthetic division, but since synthetic division only works in special cases where the denominator has degree 1, and really optimally when the leading coefficient is 1, I'm going to just do the long division because it's probably going to be the one you'd have to use in most other cases. Because remember, long division works in all situations. Synthetic division is the shortcut. All right, so to start, I'm going to ask myself, what times x gives me x squared? The answer is x. I multiply that to both parts of my divisor, and then write the answer below, and then subtract down. X squared minus x squared is 0. -4x minus 2x is -6x. That's the place where most students are going to make their mistake, is they're going to forget the subtraction is distributed. Make sure they're subtracting all the terms. We'll bring the -5 down, and then repeat and ask ourselves, what times x gives us -6x. That is -6. So again, multiply that to both pieces of the divisor. Subtract down. -6x minus a -6x is 0. -5 minus a -12 is 7. So that I have a remainder of 7. So what this says then is that r of x could be written as x minus 6, that's the quotient, plus 7, the remainder, over x plus 2, the divisor. Now the piece that we care about is the quotient. That's going to give us our asymptote. So the remainder doesn't tell me any information about asymptotes on the graph. The piece that I care about right now is the quotient. Does that remember that from last year, my dudes? Yeah, okay, good. For sure. Okay, the zeros. I'm going to write this down in the factored form since we already factored it earlier. I know that's going to make the solving pretty trivial. So I get 5 and -1. The y-intercept, I'm just plugging 0 in. That gives me 5/2. And then obviously no reducing, so no removable discontinuity. Any questions so far? All right, let's get a graph in here. All right. So let's see, what do we got here? -2, and then 5, 6, 1, 2, 3, 4, 5, 6, 2, 3. All right, so I start graphing things. I have a vertical asymptote at -2. I have a horizontal, or I have an oblique asymptote here at y = -6. So to plot this, I'm going to just pick some values for x and find their corresponding values for y. So I picked 6 and 0. So when I plug 6 in, I get 0. I plug 0 in, I get -6. So there's my oblique asymptote there. Extend those out a little bit more so I have a little bit better picture. Did I write 5/2? That should be -5/2. How come none of you guys yelled at me for that? Makes more sense. Jeepers creepers, guys. You gotta hold me accountable when I start making mistakes. Somebody's gotta be paying attention here. All right, so I plot the 2 zeros and the y-intercept, and we should be able to tell then that this part of the graph has to look like that, right? I just have to check then whether my other piece should go in there or there. Everybody agree? So I'll just do that the same way, figure out whether we're pointing up or down on the left-hand side of that asymptote. So we'll look at -2.1 and then -2.01. So at that point, I'm pretty positive what's going on, that I should be down in that lower region. So there I go. What do you guys think? Not too bad, right? Hopefully that feels reasonably familiar. All right. The next section we're going to do is look at solvings. So there's no like theoretical information here. This is just going to kind of recount some of our solving techniques we can use, run through some examples, and get out of here. So, first equation, we're going to look at x plus 3 over x equals 4. What's one way we could go about trying to solve this thing algebraically? Don't say type it in my calculator and graph. Although that's not invalid way to solve it. I'm looking for algebraic techniques, though. What could we do? They are.
Oh.
What's up?
Check that off the list.
Check that off the list. Luke?
You could multiply by x to get rid of that x.
Yeah, that's a great idea. So this would be like, I call this idea clearing fractions. So basically what Luke's going to do, multiply both sides by x, is going to get rid of all the fractions in our problem and change this now into a polynomial equation. And then we can move everything onto one side. What you see is a quadratic with leading coefficient of 1. I would try to factor this. Two things that multiply to give us 3 and add to give us -4 are -3 and -1. We can apply the zero product property here. And when we solve, we get 3 and 1. Is that it? Yeah, so that we do need to check for extraneous solutions. We don't need to necessarily go all the way to checking to see if they work, although that's fine to do. All we really need to do minimally is check to make sure they don't give us a 0 denominator anywhere. So plugging 3 back in, obviously none of those are going to give us a 0 denominator since our denominator is just x. So that's it. Alternatively to what Luke did, there's some other things you could do. You could subtract x from both sides, which would create a ratio, and then that's one fraction equal to another fraction. When you have a ratio, you can cross multiply as a solving technique, which will get you to a polynomial, and you can do the same thing that we did before. Everybody's okay with that? Another option is you can make a common denominator to both sides. If you do that, then you can just set the numerators equal to each other and go from there. All three of those are valid ways to solve really any rational equation like this. I typically prefer the clear fractions. I find it is usually the least amount of algebra that I have to do. And I like it because I get rid of the fractions the soonest I possibly can. I don't have to monkey around with those things. Because in particular, like adding and subtracting fractions can be kind of a hassle compared to multiplying fractions. We'll do a couple more examples and then go on about our day. All right, so here we have x minus 6 over x plus 1 is equal to 0. What do you want to do here? Yeah, that's what I would do. Multiply both sides by x plus 1. That'll clear the fractions. Don't need to, whatever. So that gives me x times x plus 1 minus 6 is equal to 0. Again, what I'm left with is a quadratic. Leading coefficient is 1, so I'll try to factor. Two things that multiply to give me -6 and add to give me +1 are +3 and -2. So when I solve that, I get -3 and +2. Do both of those check? What do we have to look for? Just whether it gives us a zero denominator when you plug it back in, right? -3 is fine. +2 is fine. So both those solutions are good. It's good.
We need one more volunteer. One more person on the list. We need one person. I will give you 1 minute to decide on if you're going to break or not.
Okay. Next one up. What you want to do here? Lily?
Write down the quadratic.
Factor the quadratic on the right. Yeah, that's an excellent idea. Because right now it looks kind of rough. However, if you factor that, that makes a big diddly darn difference, right? So if we wanted to clear fractions, what could we multiply both sides by? Lily?
X minus 40, x minus 1.
Yep, x minus 3 times x minus 1 will do. Everybody's cool there? So distribute things through, combine like terms, and move everything onto one side. Again, we're left with a quadratic. This time the leading coefficient is 2, though. Remember, to factor something like this is sometimes a little bit more difficult. If you want to do it systematically, you're going to have to do that factor by grouping thing. I usually don't even hassle with that. When I see a leading coefficient that's not 1, I'll just apply the quadratic formula because it's really going to be no slower than the long factoring at that point. Although if you see exactly how that's going to factor and you think it's easier to just kind of guess and check it, you can go ahead and do that. So -5 squared is 25. 4 times 2 times -3 is -24. 25 minus a -24 is 49. The square root of 49 is 7. 5 plus 7 divided by 4 is 3. 5 minus 7 divided by 4 is -1/2. Do both of those check? No, right? 3 is a problem. Why is 3 a problem? Yeah, when I plug it in, I get a zero denominator. Does it matter if it happens 1 time or 2 times or 3 times? No, it just has to happen once, man. That's all you need. You get one undefined thing and you are in big, big trouble. Of course. All right. One more example and we'll move on to the next topic. Put on your imagination caps because you guys are all turning into farmers. Yes. You want to build a rectangular pen. That pen needs to have an area of 500 square feet. And because you are a cheap farmer, you want to use the minimum amount of fencing necessary. Or you're efficient. What are we going to be doing here? Well, what is the fencing going to be the same as? The perimeter, right? So let's name the sides. I'll just call them L and W. Everybody's cool with that? And I know then the area is length times width. And that's got to form a system of two equations. Both those two things need to be true, right? So what I'm going to do is I'm going to solve the area equation for either L or W. It doesn't matter. And then I'm going to plug that into my equation for perimeter. And what I've really done is created a function for perimeter in terms of W. So I'm going to then go to my calculator and graph this function and find the minimum. I do need to be a little bit careful about this, though. What do I need to be careful about when I'm doing that in my calculator? Are all values of x plausible values in this situation? No, man. What kind of numbers are implausible? Negatives. So we're going to be a little bit careful when we create our window. Since x is representing w, and w is a measurement, I know w cannot be negative, so I'll go with an x minimum of 0. And then I chose 500 for the x max because I figure a 500 by 1 pen will not minimize the fencing. That's a pretty crazy looking pen, but it's like a realistic, like value that it could have. And then the perimeter, again, 0 is the minimum amount of fencing. Now I know it's going to be bigger than 0. And then if I did the 500 length, or a 500 for width, the length would have to be 1, so the perimeter for that would be 1,002. So I just wrote 1,000 because I know it's not the answer. And I'm going to hit graph. So there's my function. Looks like my minimum is somewhere over here. So to find that, I'll do second trace, minimum command. I'm going to trace this over until I see the y coordinate stop getting smaller, or I run into the vertical asymptote. So still getting smaller, 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 smaller. Oh, got bigger. But like 2 more buttons and I'm at the asymptote. So I'm just going to use the asymptote as my bound. And then my right bound, I'm just going to keep moving until, the y coordinate's been getting bigger for a while. It's going to keep on getting bigger. I'm going to stop here. That's good enough. And hit my guess. So it says that my W is 536, and the perimeter then would be 2236. I don't know, why did I say 5? I don't even know. And then 8944 for the perimeter. I think that was 8944, wasn't it? Yeah, okay, good. Just in case I need to tell my farmer specifically, if this wasn't enough information, he needed the length too. How would I find the length? Yeah, very good. Guess what I get when I do that? What shape is this figure actually turn out to be? Yeah, it's a square. Now, who's surprised by this? Hopefully none of us, right? If area is held constant, the shape that minimizes the perimeter is always going to be the regular figure. So now if you had a tricky situation where like, oh, I'm going to build one side of my fence against this wall, so I only need 3 sides of fencing. Now you're not necessarily guaranteed to have to need a square. You know what I mean? But if it's just like any old pen, you know, that's your regular figure is where it's at. You guys remember that from your candy project in geometry? That those of us that took geometry did the candy container project? Did you take the honors geometry course? You remember doing that? You might not have done that. Oh, because of COVID. That's right. Yep, that would have been a second semester thing. Probably got canned. Yep, you're right. That's a project you missed out on then. It happens. All right. The last section we're going to be talking about is going to be solving inequalities. So let's say we have, again, nothing theoretical to discuss here. It's just going to be some examples and kind of talking through some of the little ins and outs of these examples. So we have x squared minus 4 is greater than 0. How many solutions does this have? No. Infinitely many. Why? Yeah, it's an inequality, right? It's a lot more than 2. So our answer here is always going to be like describing a set of values. We're going to be using interval notation to do this. What we need to do then is figure out where these intervals could begin and end. Now, for a continuous function like a polynomial that has no discontinuities in it, the only place where our function can change from negative value to positive value is at the zeros. And how many zeros are there going to be? 2. So that's what we're going to start by doing, is finding the zeros for our function. And I find it quite helpful when learning to do this to kind of draw myself a picture on the number line, to just draw what my solution set's going to be. So I'm going to start now by putting either an open circle or a filled circle at both -2 and +2. Which one would I want to use in this case? Open or closed? Open. Great. Why? Yeah, since it's a strict inequality, that's telling us that we need to have the open circles. And now I'm just going to take a test value from each of those 3 sections. It doesn't really matter what the value I pick is, just as long as it's from that section of the graph. And then I'm going to plug it back in and see if it satisfies or what kind of value I get. So -3 squared is 9, minus 4 is 5. I don't really care about what it's equal to. All I really care is whether it's positive or negative. If I plug 0 in, 0 squared minus 4 is -4. Negative. If I plug 3 in, I get 5 again. That's positive. So which parts of this am I looking at? The positive parts or the negative parts? Which ones satisfy my inequality? Lily? Well, positive parts, yeah. So I want those 2 sections. So I'll say x is a member of -infinity to -2, union 2 to positive infinity. Done. So I find the little number line picture to be quite helpful, in particular for picking my test values and making sure that I've got all the sections covered. Let's do another. Okay, what do I want to start by doing? Yeah, I want to find the zeros for the function, so I'll start by factoring off an x. I notice that the remaining quadratic also factors. Oops. So when I solve this, I get really just 2 solutions, right? Even though there's 3 answers. Since I have a duplicate, that's okay. Okay, should I be drawing open or closed circles here at 0 and 2? Closed. Why? Yeah, we have the or equal to inequality. So I'll pick some test values. Okay, -1 cubed is -1. That's going to be -4, and that'll be -4 also. So all those are a bunch of negatives. That's negative there. Put in 1, that's 1 minus 4 plus 4, so that's positive. That's 27 minus 36 plus 12, that's positive also. All right. Everybody cool with that? Again, I don't really care what it evaluates out to at those test values. I just care whether it's positive or negative, really, right? Okay, so which parts of this interval, or which intervals constitute my solution? Just this part, right? Is that right? Ugh, come on, you stupid pen. OneNote wants to fight with me today. Oh, it's all just frozen up, period, huh? Whole computer's frozen, apparently. What's disturbing me the most is this flashing. That doesn't feel like that's a good thing, right? Oh. It might have caught up here. No, still wants to fight. I just don't get it, guys. Does this happen to you? Or just like, nah, I'm good. All right. OneNote. Let's do it the hard way. Are we going to restart here? All right. Okay. So we would write this, right? That's our answer. Everybody agree? And that's not right. We missed something. Luke says, no, we didn't. I promise you we did. We missed this spot. Right? That's also, the function is equal to 0 there. Oh, Mr. Kulik, you sly dog. This is why I was so disappointed when my computer stopped working. I got right to the payoff. Where it's like, I'm going to trick everybody right now. And then I get to like string it along. Ugh. We see why that point also needs to be included though. If I plug 2 in, that is equal to 0 there. It satisfies the inequality. Because it's a closed circle, we had to count it. If this was a strict less than, then no, we wouldn't need it. Does that feel a bit better? Yeah. Sneaky, right? Sneaky stuff, Mr. Gulick. Again, this what we're doing right now I don't think is terribly difficult, but there's lots of little sneaky things that can happen. All right. Uh-oh, what happened here? It's not a polynomial this time, right? It's a rational function, which means that it can have discontinuities. So now, instead of only being able to change sign at a 0, our function could also change signs at the discontinuity. So, for example, we ought to take the zeros and the discontinuities. Everybody's cool with that? And you're like, well, that's not... I don't know why I'm putting those labels on there. Put 0 in there. Okay. All right. Positive 4. Filled in or open? I don't know. Open or closed? At 4. Closed. Because of this. -1. Open. Why? Why is it different? It's a discontinuity, right? So, it's jeepers creepers. Discontinuities are always opens, regardless of what type of inequality you have. Always open. Okay, when I plug in -2, I have -6 over -1. Negative over negative is positive. When I plug in 0, I have -4 over 1. Negative over positive is negative. When I plug in 5, I get 1 over 6. Positive over positive is positive. So, am I looking for the positive parts or the negative parts in this one? The positives, because it's greater than. So I'm going to need -infinity to -1 with a parenthesis, and then union bracket 4 to positive infinity. Notice that one of them is a parenthesis and one of them is a bracket because one of them is filled and the other is open. Oh, Mr. Kulik. So mean. It's not that mean. Last one. We're done for today. Yay! All right. Square root of x plus 4 divided by the absolute value of x minus 1 greater than 0. If okay. So same thing, find my zeros. What's the solution to square root of x plus 4 equal to 0? -4?
Negative.
Yep. Yeah, I would write that answer down as soon as my OneNote wants to respond. OneNote, I hate you so much. Actually, I just hate my whole computer today. Oh my God. I noticed that my OneDrive is just flashing intermittently again. Oh, task manager not responding. That's quite helpful. You're supposed to be my savior, task manager. What is your problem now? I'm pretty sure I have more than just sticky notes running. I just want to quit. Can we just, computer, I hate you so much. Is this gonna work? No, nothing wants to work. I can't even, where's my mouse? You are the problem, stupid OneDrive. I know you are. Yeah, quit. Go away. Don't come back. Yes, go away. Nobody uses you. There, that was the whole problem. Now everything seems to be fine. OneDrive, oh no, I lied. No, I didn't want to do that. Do that. Is that, no, still not working. I'm going to throw my computer like a frisbee. Try this one more time. We're literally like a minute from being finished, and we can't finish because it just wants to fight. Okay. All right. How many solutions are we going to get to an absolute value equation? Sometimes two, but in this case, the two solutions turn out to be the same, right? When we set our absolute value equation, one is positive, one is negative, but if it's equal to 0, positive 0, negative 0 are just both 0. So it's really just 1 in this case. Okay, at negative 4, open or closed?
No, open.
Open. At positive 1, open. Pick my test values. When I plug positive 5 into the numerator, what do you notice happens? Yeah, I get an imaginary result. So that's just really undefined because we know that there is no inequality defined for imaginary numbers. Plug 0 in, I get 2 over 1 positive. If I plug 2 in, I get square root 6 over 1 positive. So that's my answer, right? So I can just write it like this. Everybody agree with that? Good. You should not. What's the problem? Got that open spot at 1, right? Tried to trick you. You guys saw through my trick. That's great! I'm glad that you did. All right, let's stop here before I actually have to throw my computer. We did do all of chapter 14 today, so we are a day ahead. That's great. We're going to do chapter 12 tomorrow, and then Friday we'll just kind of be able to... Sound good? All right.